This is our What the Physics video. This one is continuing on with simple harmonic motion. We are going to be focusing on, well, we're going to deal with graphs and talk more about the things we had discussed before in terms of how the concepts relate to each other in terms of like force and acceleration and velocity and right here, timing. So we've got our vocabulary on timing we had actually discussed earlier, period, frequency, and angular frequency, which is a bit new. So we're moving on and we are practicing, there we go, practicing our timing. So pendulum completes 10 swings in 8.0 seconds. So what would its period be? Yes, sir.
8 over 10 and 28 seconds.
Okay, so we are always going to be dealing with decimals in physics. Well, I'm going to say for the most part. I shouldn't say always, especially with the upcoming topics. But yes, in general, we do prefer decimals, so that'd be 0.8 seconds. Yes, lovely. Okay, part B, calculate its frequency. Frequency would be, yes?
1 divided by 0.8 should be 1.25 hertz.
Okay, so it is, remember, period and frequency, they're just inverses of each other. So if you already have the period, you just say 1 divided by that, and 1.25 hertz, or with sig figs, maybe 1.3 hertz. Yes, good. Okay, remember, hertz is the same thing as saying swings per second, yeah? And then calculating its angular frequency. Angular frequency. Remember, what's the difference between just plain regular frequency and angular frequency? We gotta just multiply by 2 pi, right? So take our 1.25 and then multiply by 2 pi, right? But we're not going to say such and such hertz anymore. We're now going to be saying radians per second. So it's 7.8 radians per second. Okay, good on that? Making sense? Hopefully? Yes. All right. It's important that we practice these at least a little bit because we're going to have all these little tiny equations and relationships like, oh, fair, this one is, this is talking about period instead of frequency. Oh, well, that's easy enough to do. Okay, if I didn't have you solve for the frequency, could you still solve for the angular frequency? Yeah. You just say period divided by, right? Or, I'm sorry, I messed that up. You would just say 2 pi divided by the period, right? It would be the same. Okay, so what's with the radians? Aren't they evil? Well, I should say they. Aren't they evil? Yes, but they are necessary. If we hang a mass from a vertical spring, just like we had done in the beginning of the year, we can then pull it down and cause it to oscillate. What types of patterns are we going to get? Now, before I even do this, what do you think is going to happen? If I have a hanging spring, like right here, okay, and for those 5 people that are watching this video at home, okay, I have this mass hanging from a spring. If I bring it down and I release it, what's going to happen to the mass? It's going to go up, right? Okay, and it's just going to stay up there, right? No. Okay, it's going to go up and down and up and down and up and down and up and down, right? Okay, not a big surprise because that's what our PhET simulation was showing us, right? Okay, now what would happen though if I took a motion detector and had that right underneath this oscillation pattern? What would it show us? Well, it would show us this. Okay, here is a position time graph, here's a velocity time graph, and here's the acceleration time graph. Okay, what do we notice about what they look like? They look like sine and cosine waves, right? Okay? Or if you want to be really fancy, you can say they're sinusoidal. Okay? That's an actual word. Okay? Although you have to spell it reasonably correctly. I remember actually it was in high school physics, and I had said sinu or sine sortal or something, and my teacher was like, sort of sine? I don't know what that means. I'm like, oh, you know what I mean. So, good times. What do we notice about the position time graph and the velocity time graph and the acceleration time graph? Specifically, you say, well, they're all the same shape there. Well, yeah. Okay. Because they're sinusoidal. But are they identical? Okay. So, how do they vary? If I look at it, let's say, unfortunately, it doesn't line up perfectly, but it's reasonably close. So just before 2 seconds, the position here, it's at its highest point, yes? Okay. Just before 2 seconds, is that where my velocity is? No. Is that where my acceleration is? No. You say, oh, well, shoot, I guess there's no pattern at all, right? Kind of is. As I said, just before 2 seconds, maximum displacement. When I'm at my maximum displacement, and you can refer back to the previous slides, what is my velocity looking like? If I'm stretched out as far as I can go I go any farther? Have I started to come back in yet? So for a split second, what is the velocity? 0, okay? This is just like when you throw a ball up in the air. Okay, at the highest point, the y velocity is 0, but just for a moment. Okay? Now I say it's just like that, except for it's a continuous back and forth. Okay, but this moment is just like that. Okay? Now what about the acceleration? What do we notice about the acceleration just before the 2? Okay? That's at an extreme as well. However, it's at a negative extreme. And if you recall from our diagrams, and if you don't, look back at them, when I'm at my positive amplitude, my max amplitude, what is the direction of the force? Is it in the same direction? It's in the opposite direction. And remember, acceleration and net force are always going to be in the matching up direction. Yeah. So if I have my largest positive displacement, I'm going to have my largest negative acceleration and negative force. Okay, that's going to be super important here, folks. Okay, this is a larger version of that. Okay, came from the textbook, but fine. Okay, if we take a moment to look at this guy versus this guy, it was nice because it started off right at time 0. If I had to name this curve versus this curve, how would I distinguish those, do you think? I can say both are sinusoidal, but specifically I might say this one is say again? Cosine, okay? And then this one is a sine. You say, oh, but it's a flipped one. Oh, who cares? Yes, sure. Okay. Okay, and then this one is a cosine, but you'd say it's flipped, or you could say negative, right? Okay. All right, good. So, moving on. Remember early on in the notes, it was the second slide, I believe, I had said, hey, we're not allowed to use the big 5 equations. And you say, oh, fair. Please don't bring that up again. The pain it's just too raw. I can't handle it. But okay, sure. But I did also say that we'd be able to use the slopes. So what I'd like you to do is look at this graph again. This is just a zoomed in version of the other one. Here's the position time graph and a velocity time graph. I'd like you to take a moment and point out the maximum slopes, both positive and negative, on the position time graph. Mark them on your papers. And then also mark in where the slopes are 0. Okay, so take a moment to do that, please. Okay, so what I did was I marked them in black and red. What is the red? The steepest negative. Okay. What happens when I'm at my steepest negative? Okay, that's when my velocity is largest, negative. Okay. Likewise, and so on, right? And then in black, that's when it's what? Steepest, positive, okay? Okay. Okay, and so on. Oh shoot, I forgot to mark the last one. What was it I was also supposed to mark? When the slope was 0. So that's going to be like right here, and here, and here. Oh, look, they already made the dotted lines. Oh, that's interesting. That's when the velocities are 0. Okay? We've done this type of thing before. It wasn't with such a curvy graph, but we've certainly talked about going from a position time graph to a velocity time graph, and we said, oh, okay, pretty smooth, right? Heck yeah, it is. Okay, in fact, we even had a guest lecturer that day with strawberry shortcake. Remember, strawberry shortcake says 0 slope means 0 velocity, right? Okay. I see a couple smiles. Good times, right? Okay. Okay, and then we also had Elmo and Optimus Prime reminding us of these things as well. Okay. And then it also goes, if we wanted to do from velocity to acceleration, we'd do the exact same thing. Yes? Good stuff. Okay? Not only velocity to acceleration, but once we have just one graph, we can keep making other graphs. We can make a force time graph. So okay, well that's pretty much just the same as the acceleration time graph, just with different amplitudes, right? Yes? Yes. Okay, fine. We can also make for the different energy time graphs. You can make a gravitational potential energy. We could make kinetic energy, right? So how would you do that? What is kinetic energy based on? Mass is constant. The 1/2 is constant. The velocity, specifically velocity squared. Okay. So what would this look like squared? Yeah. Okay. Well, for one thing, would it have anything downstairs? No. No. So not only would the values be larger, okay, although of course the amplitude might vary anyhow because it's a different thing on the y-axis, but it would all be just the tops going like this. That's what a very simplified version of the kinetic energy would look like, right? Okay. Good stuff. Cool. All right. Actually, you know what? I'd like you to take a moment and try some of those. Okay? I'd like you to use this information, and you have some graph paper in your notes there. Go ahead and sketch these graphs out real quick, and then make a force time graph. And try to make a kinetic energy graph. Okay, so hopefully we've got some good progress. Oh, not that. Not it. We have this, there. We have this graph here, and we already have the velocity and acceleration done from the position time graph. So what else can we draw? There was a force one, right? So how is force related to any of these? Same as the acceleration in terms of type of graph. In other words, the acceleration, well, I'll just draw, it's not going to be really beautiful, but it's okay. Trying to line these up reasonably well. Okay, so where does the acceleration start off at? It's in the negative, in the extreme negative. So that's where the force is going to start off as well. Okay, and then it crosses through the axis, and it's going to be up here, right? But you got to do a little curvy action to it as we go through. Okay, and then it crosses through the axis, and then, right? Okay, and you say, well, okay, so fair, how is this different from the acceleration? Because it can be slightly different, depending on what you chose. What I chose. How is force slightly different from acceleration? There's an equation relating them. Are they the same thing? No, it says F equals ma, yes? Well, I guess I should probably label these things too, by the way. This is force and this is time. Okay? Said, yeah, fair, that's what I was wondering. I was trying to figure out what the mass was. You never told us what the mass was. I don't know. 1, 10, 50. It's not going to matter in this type of graph because I don't have any actual markings on the y-axis anyhow. So if you drew it really tall, great. If you drew it kind of short, great. Same thing. As far as we're concerned. As soon as we get some values, then we could actually plug in like, okay, at this moment it has to be up here and so on, right? Okay. What else can we do? We drew the force. What else? Yes? Kinetic energy versus time. Right. Which one is that going to, I'm not going to say mimic, but, reasonably copy? We said the velocity, right? Let's see if I can, I wouldn't be able to grab that, can I? Okay, well, I'll just bring this down here. We've already seen that one. Okay, so we'll try for this. So there's kinetic and there's time. And as we said, boom, just continuing these guys downwards. Okay? Where does it start off at? At 0. Okay? And it goes upwards. Why? We already mentioned it. Remind me. Because it's velocity squared. Okay? So, oh, but fair, you never told us what the mass was. Hey, just like before, I never told you what the mass was. I'm going to say the mass is 2. Why? Because I'm about to multiply it by a half. And that just makes that all go away, right? Okay? So I'm really just going to be saying the velocity squared. Okay? So it's going to end up looking big like that. Okay? When the velocity is 0, the kinetic energy will also be 0. When the velocity is at its maximum, either positive or negative, the kinetic is going to be at its maximum, but it's always going to be positive. Okay, something along those lines. Okay? Right. And then what about the other types of things? We can do, well, I guess we could do momentum, but we don't really talk about momentum, so let's not bother with that. Gravitational, well, it depends on what type of thing we're talking about. I believe this was originally a horizontally moving object, so that means there's not going to be any change in that, so it's just going to be a nice horizontal line. Okay. If it were a vertical spring, yeah, that would be changing all the time. Okay. If you look back at your PhET simulation, you can turn on the energy bar charts, and you can see how they're moving. And it's really cool because the total amount of energy is constantly changing. I'm sorry, excuse me. The total amount of energy is constant, but the individual pieces are constantly changing. So if I were to draw a total energy time graph, just say like mechanical energy, I'll just do like that. Okay? And when the mechanical being consisting of kinetic and elastic potential here, when the kinetic is largest, what do we already know about the elastic potential energy? It's going to be at the smallest, right? It's kind of harder to draw those, so that's why I like the bar graphs, but you should at least be able to recognize the general shape here. Yes? Right. Okay, cool. Let's move on. Let's do some trig. Okay, so we've got, you all have learned about unit circles, right? When do you do that? That's in, like, beginning of trig. Is that correct? What do you guys learn about the unit circles? Anything in particular? Like, you know, like what the radius is, right? Okay, so if we have this guy is the radius of the circle, I can express that radius in terms of the x and y pieces. Yes? Just, I'm hoping familiar. Okay. I can express it in terms of x and y pieces. We actually did this earlier on in the year, right? If I'm launching a ball at some angle, I can find the x and the y pieces of it. Yes? Okay. Great. In this case, if I just say, hey, my radius is 1, then I can just say, oh, my x component is 1 cosine theta, or just cosine theta, right? Likewise with the sine, yeah? Okay. Now, that's kind of cool if your radius is 1, but what if it's not 1? What if it's some unknown value? What if it's like, you know, a, or we could use r if we wanted to. Then we just keep that value in the front. Okay? If we have a here is the radius, then I'd say, okay, that's fine. I can express it, I can express the x piece and the y piece by multiplying by sine and cosine. Okay? Can you guess why I said a up here, by the way? A stands for, you don't have to whisper though. Amplitude, yes indeed, thank you. Okay, standing for amplitude. Okay, and you said, all right, I sure. What do you want with that though, Fair? Well, I'm going to change this equation up a little bit. We're used to seeing a cosine theta or a sine theta. But instead of using theta, I'm going to use something else. Okay? Let's just make sure we understand. And we talked about this a moment ago. It's a sine wave when we start from equilibrium point, and a cosine when we start at like up here, right? So this is a cosine wave, yes? And this is a sine wave. Okay, instead of using theta, I'm going to use omega t. You doing okay so far? Okay. Think of this, and when we talk about rotational motion, it will be a lot clearer when we get back to that point. We can think of rotational motion as very, very similar to linear motion. Instead of regular velocity, we have angular velocity. Instead of distance traveled, we have angle traveled. Okay, so this is like saying distance equals rate times time, except for with angles. Okay. Anyhow, I'm going to take out that theta and put in its place something different. Okay, I can put in any one of these. I can put in omega t. That's a lowercase t. Remember, that's unknown time. Or I can put in, instead of omega, I can put in 2 pi f, or I can put in all these guys. Okay, so I can express this function here various ways. I can say, oh, x is equal to x naught, that's the original, sine omega t, or I could have just said theta, right? But I'm going to say sine omega t, or sine 2 pi frequency times time, or sine 2 pi lowercase t divided by capital T. Remind me what capital T is, please? That's the period. Okay, so remember what I was saying earlier on. I said you got to remember these little tiny equations. You got to remember that period is the inverse of frequency. You got to remember that angular, that the omega guy, is frequency times 2 pi. Because really, these are all just the same equations. I don't want you to have to memorize 6 different equations. In fact, it would be a lot more if we do velocity and acceleration from here. I don't want you to have to memorize dozens of equations. I just want you to be like, oh, that's the same thing as saying this. Fine. I can handle that. Okay? Now, you can also convert from sine to cosine by doing this, but I don't really want to have to handle that. That's a bit of a just nuisance in my opinion. But we're going to try an example problem. Okay? So feel free to look back at the previous slide. But take this curve, figure out what is the amplitude, what is the period, what is the frequency, what is the angular frequency, and then write the displacement function. You say, how should I write it fair? Should I write it so it's like 2 pi ft? Should I write it as, you know what, you decide. You decide, because then you're going to have to calculate the displacements for these times. Okay, try it out. Okay, so first of all, what is the amplitude? 0.08 meters, right. In this case, we're talking about the value on the y-axis. Now, always be careful, and something I mentioned way back at the beginning of the year. Anytime you're dealing with graphs, you always look to see what type of graph it is first, before you jump in and say, oh, I got to divide, I got to count, I got to do this or that, right? Okay, so if you weren't careful, some of you might have been like, wait, this is the x-axis? What is that x referring to there? It's displacement on the x-axis, right? Okay, so like I said before, this would be a horizontally oscillating spring, right? Okay, good. So, but the point is, this is the displacement. So, I just have to figure out the maximum value there, and there I go. And the period. What's the period?
4 seconds.
Okay, 4 seconds. And you know what? I got this on the DPD. And the frequency is just the inverse, so that's going to be 0.25 hertz, yeah? Okay, and then The omega is what? So that times 2 pi, right? Okay. Which is this pi halves. Okay. So in the past, I would say don't leave things in terms of pi. Give me a decimal answer. Okay. When we're dealing with vibrational motion and angular motion and such like that, you'll want to leave things in terms of pi. So for those of you folks that plugged in, 3.14159 divided by 2, and okay. For this case, leave it in terms of pi, especially if you're going to be plugging back into an equation and such. All right, and so what's the displacement function going to be? Well, what type of graph is this? Is this sine or cosine? It's a sine graph, okay? So we use the sine, so I use the x naught sine omega t, the lowercase t, right? Okay, so I just got that. Okay, so when we do this, we're going to take the sine of this whole thing. Half of pi, you could also say 0.5 pi if you wanted to, times t. But then when we start plugging things in, as in number 2, we might see that some of these fractions actually cancel each other out. So let's look at that. If time is equal to 1 second, all I've got to do is plug this in. I got to say 0.08 sine, parenthesis, pi over 2, and then times 1. Okay. Remind me what pi halves is in terms of degrees. Say again? 90 degrees. Okay. What's the sine of 90 degrees? 1. Okay. We've discussed that a lot already. Same as, obviously, sine of pi halves, right? So some of you might have even said, hey, I don't need to punch this into my calculator at all. I can do this in my head. Cool. But, if not, use your calculator. No big deal. I'd get sine of this business as 1. So I'm just going to say the answer is 0.08. Good stuff. Okay. It's handy if you're doing this with your calculator and you set it up like this. I always put the little t at the very end, so that way I can just recall the equation and change that little t if necessary, if I'm getting several values, right? So 2 seconds. If I put in the 2, some of you folks, once again, can do this in your head. You'd say, oh, well, 2 times pi halves, that just means pi, right? Sine of pi, or the sine of 180, is 0. Okay? And then 2.5. You say, well, maybe you can't do that one in your head. Okay, sure. Plug it in, no big deal. What do we get? Say again? Negative 0.707. I'm not sure about that. Try it again. Okay, maybe I misunderstood what you said. I got this value. Negative, there's this negative sign that's kind of hanging out over here. So it's negative 0.057. Is that what others got? Okay, good. All right. If you're not getting this, though, please try it out again. Maybe you plugged in something wrong. Like I said, you do have to be in radians. Okay. Could be an order of operation thing with your calculator. Now, realistically, if you said sine parenthesis pi divided by 2 times 2.5, your calculator will not automatically assume that 2.5 is in the denominator. So even if you forgot some parentheses, you should still be okay. We okay now? All right, good. Okay, so definitely got to be in radians. We've gone over to the dark side. Okay. Now that we've practiced our pre-calc skills, let's move on to our calculus skills. You say, what? There? What are you trying to pull here? Don't worry. It's like one slide worth, and it's going to be the easy stuff. Okay? We're just going to deal with basic derivatives. Recall, please, when you were, guys, when you were learning about just basic curves on a graph, you know, straight lines, maybe a little curve to them, horizontal lines, all those things, we would take the slope of the position time graph to get the velocity time graph. You take the slope of velocity to get acceleration. Yes? Okay. That, in very simplistic terms, is a derivative. In math class, you're going to learn all sorts of fancy pants versions of the chain rule and use substitution, and it's going to get intense. We're not going to talk about that right now. Okay? All we're saying is, hey, this divided by that, derivative. Boom. Okay? Integrating is when you go the other way, when you multiply them. Okay? Like the area under the curve. Right? Okay. And you folks that are in calculus, you know that whenever you do an integral, you always have to add on a constant, right? Okay. We actually did that when we were doing the area under the curve as well. Whenever we found the area under the curve, say we found the area under the curve of an acceleration time graph, we found the change in velocity. We didn't find the actual velocity, we found the change in velocity. If we added on a constant, what we'd be adding on is the initial velocity. So if I take the initial velocity and add on the change in velocity, I get the final velocity, right? That's what I'm trying to say right here. Okay? So you say, great, Fair, why are you telling us this? Why are you trying to confuse my mind? I'm just trying to get you to see how sine and cosine are related to each other in terms of derivatives. If we start off with a sine curve, and we already saw this with the graphical, that's why I pointed it out with the position time graph to velocity time graph. We start off with a sine curve, we take the derivative of that, in other words, we do the slope, it becomes cosine. Oh, it's kind of blurry, it's weird. All right, this thing means derivative. Derivative of the sine gives us cosine. Derivative of cosine gives us negative sine. Okay? Just accept that for a moment, because now we're going to move back to those graphs. Okay. What type of graph is this again? I forgot already. It's a cosine graph. How do you go from a position time graph to a velocity time graph? You take the slope, you do the derivative in our fancy words. What's the derivative of a cosine? Negative sine. This is a sine, except it's flipped, so we say negative, right? Okay. It's a sine graph. What's the derivative of a sine graph? Cosine, except it's a negative sine graph, so it's a negative cosine graph, right? Okay? So that's why it looks like this. So for those folks that are already comfortable with derivatives, you've done this before in your math class. For those folks that are still a little squeamish, okay, I'm just pointing this out. So you can immediately recognize how to go from one to another. We already spoke of it in terms of physics. We already spoke of it in terms of, hey, when I'm at my largest amplitude, or when I'm at my largest position, right? To the right, we'll say it's positive. That's when I'm not moving, but that's when my acceleration is going to be the largest, but it's in the negative direction, right? Okay. And then as I'm moving back forward, this is in my equilibrium point. That's when my velocity is the largest and my acceleration, excuse me. That's when my velocity, I'm pointing at the wrong thing, excuse me. This is the equilibrium point here. That is when my velocity is largest in the negative direction. And that's when my acceleration is 0. Okay, so same stuff I talked about before. That's why I spent a little bit of extra time on it. So this time it would just, kind of settle in a little bit more. Okay, so I'm hoping that we can notice stuff now that I had already mentioned. We know that force and acceleration follow the same pattern. We already did those graphs. We know the amplitudes may not be the same, but the shape will be the same. And as we said, the acceleration is the flip of the displacement. Once again, different amplitudes, but same shape. One is a positive sign, the other one is a negative sign. Or one is a positive cosine, the other one is a negative cosine. Okay, we already talked about that. So this is kind of summarizing all the concepts that we've discussed. We saw this already. The amount of stretch doesn't affect the period. Okay, you can think of it as the more the spring stretches, the more the spring potential energy, right? Okay, and that's all going to turn into kinetic energy, which means a bigger stretch means a bigger US, means a bigger kinetic. That means it's going to go faster, right? Okay, just 1 second. Larger V, so it's going to go a larger distance in the same amount of time because it's going faster. That's why the amplitude doesn't actually affect things. So, what's the equation for a spring? There, okay? Good stuff.